Okay, so last time we talked about holonomy and flux. So we know that on the lattice, we have lattice variable holonomy and flux HE and PEJ for every E being the edge on the lattice. Okay, and also we have so these are lattice field, and well, they belongs to the phase space on the lattice, which is SU2 cross R3 to the power number of edges. Yeah, so as I said, this is also usually denoted as the cotangent bundle of SU2. Okay. Also, we have lattice gauge transformation TV for every vertices. Gauge transformation. So yeah, it belongs to SU2 and to the power number of vertices. Yeah, because each gauge transformation at the vertex is an element of SU2. Okay. All right. So end of the last lecture, we also talk about I give you the formula for the Poisson brackets between those lattice variables. So this is usually called Holonomy flux algebra. So I list it as a theorem. So this is Holonomy flux algebra. This is just a Poisson algebra between H and P. Flux algebra. Okay, so firstly, H is is just 0. And Poisson bracket between P and H is non-trivial. Half times H E prime. And also you have non-trivial PP Poisson bracket. L. E. So and the last Poisson bracket I also mentioned last time is very similar to the angular momentum commutation relation from mechanics. Now, this lecture we are going to prove them. So well, so let's label them 1, 2, and 3. So 1 is trivial because both holonomy only depend on A, and AA Poisson bracket is 0. So 1 is trivial. And so here we are going to spend some time on proving Poisson bracket 2, but I will leave Poisson bracket 3 as your homework. Okay, cool. Okay. All right, so let's work on that. So, well, by definition of Poisson bracket, using Ashitaka's new variable, so you can compute the Poisson bracket by using functional derivatives. So this is a prefactor kappa beta divided by 2, coming from the Poisson bracket, fundamental Poisson bracket of E and A. Okay. And then you have functional derivative PJE delta EAI HE prime X. So here I and AA, they are contracted, they are summed. Okay. Here you have to sum over the space, three-dimensional space. And now here you can see that the last term is vanishing in this calculation because h is a function of a only. So you don't need to, it has no derivative. So this term just 0. So we only need to take into account, we only consider this first term in our calculation. Okay. And now we just need to compute the functional derivative of the flux with respect to E and functional derivative of holonomy with respect to E. This is something we compute. So let's first consider flux derivative with respect to E. Right? All right. So this equals to what we just copy the formula. Minus 2 trace. So let me call the coordinate y. H rho E y E K E y. Okay. H rho E y and Emacs. So this is, I did nothing. I just copied the formula of flux into this derivative. Okay, and then you can see that we only the flux is linear to E, so you only need to ask this derivative act on E. So it doesn't really act on the holonomy. Okay, so it equals minus 2 beta. Right? Delta E K Y delta EAI X. Okay. Okay, and you know this is just a delta function. It gives delta EA, delta KI, delta Y, and X. Three-dimensional delta function. Okay. What is right? IK. Okay. So this is a everything's easy for this derivative. Well, to simplify the calculation, let me choose a special coordinate. So because all the formula are coordinate independent, yeah, because holonomy, the definition of holonomy doesn't really depend on the holonomy, the choice of coordinate, and the definition of P also doesn't depend on the choice of coordinate. Yeah, both of them are coordinate independent. Both HE and PJE coordinate independent. Okay, so then in this calculation, we can choose a special coordinate. To choose a coordinate. What is our coordinate? It is the following. So the holonomy and flux. Holonomy is on the edge, and then flux is on a two surface. Yeah, so this is the figure I drew last time. So this is intersection point P. Okay, and now I build this coordinate y such that two coordinate axes are lying on the surface, while the other one is the other coordinate axis is perpendicular. It's transverse. So let's say transverse coordinate is y1, and then you have y2 and y3. Yeah. So and this is a right-hand coordinate. And so this is the entire edge is E, and this is SE. And by the intersection point P, it divides the entire edge into E1 and E2. So this part is E1, and this part is E2. Okay. And well, E is E1 with E2. Well, the orientation is along the Y1 direction. Okay. All right, and P in this coordinate system, P is located at 0, 0, 0. So in this, we build this coordinate so that P is located at the origin. Okay, so in this coordinate, our calculation should be very simplified. All right, so now in this coordinate, we can expand everything in this coordinate. P, so we just use this result, but expressed in this new coordinate. Right. And then you have a surface integral, and the surface integral is located at y1 equals to 0. Yeah. So this surface is defined to be y1 equals to 0. Y1 is a function in 3 dimensions, and y1 equals to 0 is defined the hypersurface. Define the hypersurface in 2 dimensions, which is a 2-dimensional surface. Hypersurface in 3 dimensions, and which is a 2-dimensional surface. So dy2 wedge dy3, because well, this is you see this is a 2 form. Yeah, I mean you're integrating a 2 form, and this it means that you have to restrict this 2 form on the surface, right? And then thanks to this coordinate, you only have 3 and 2 direction on the surface, so you only have dy3 and wedge dy2 wedge dy3. You don't have dy1, because dy1 as a differential form, when it restricts on the surface, it's 0. So you have when you write this part into coordinate, it is epsilon 2, 3, 1 plus dy2 dy3 wedge dy2 epsilon 3, 2, 1. Okay. So you have 2 terms because you have to sum over B and C. Okay, but B and C can only be 3 and 2, because dy1, when you restrict this form on the surface, it's just 0. Okay, and now you can see that when B and C has to be 2 and 3, D has to be 1. Okay, so you can just write D, replace every D to be 1. Okay, so here this it's just this delta dA is become delta 1A. So rho E Y delta dA. So now it's delta 1A and delta IK 3 Y and X. Okay.
Wait, you mean, Dr. Han?
Yeah.
You mean delta D1, right?
Delta D1. Why delta D1?
Because A equals to
A
1.
is the same A here. So
sorry. No, sorry. Yeah, epsilon BCD. Sorry.
yeah. Or I'm maybe here to be clear, I don't jump this step. Okay. Well, but in the end, it's just the delta A1, delta 1A. All right, so let's keep going. Well, you can see if these two terms just it's just the same, right? These two terms just give the same result. Well, this two term is exactly the same because this is anti-symmetric between 2 and 3, and epsilon is also anti-symmetric with respect to 2 and 3. So this is just equals to dy2 2 times dy2 dy3 wedge dy3 and epsilon 2, 3, 1. Well, epsilon 2, 3, 1 is just 1. Well, I mean, you are integrating this form, this differential form. Well, by definition of integration, and in this coordinate, you write as just dy2 wedge dy3, and as two-dimensional integral. So this is just integrating dy2 dy3. So you can just remove this wedge in the integration by using the definition of integral. And these two cancel these two in the denominator. Trace J integral at y1 equals to 0, dy2 dy3. And now these, you have this delta function yx. You have this delta 1a coming from delta dA, and you can use this delta 1k act on delta k. So tau k, you got tau I, but this tau I has to be sandwiched by holonomies. Multiply h rho e y tau I h rho e y inverse. Okay, so we close the bracket. Here, close the bracket. Okay, so this is the result for this functional derivative, and we can even further simplify this derivative, simplify this result, because we can write explicitly this delta function. Well, this delta function, you see, this delta function is delta function in all three dimensions. So firstly, for it equals to delta, well, y1 minus x1, and delta y2 minus x2, delta y3 minus x3, right? Well, now, so, but y1 equals to 0. So because we are integrating on the surface with y1 equals to 0. Okay. So the first delta is just delta x1, and for the second delta function, we can just integrate out because we are integrating dy2 and dy3. So we can integrate the second and third delta functions. So we just get theta. We can pull out all the deltas. Delta 1a, and we have a delta x1 coming from the first delta function, and we integrate out the last two delta functions. Trace, well, integrate them out, you just get 1, and replace all the y's into x. Okay, h rho e, you replace y by x, and tau I, h rho e x. Okay, so this is the final result of functional derivative of flux with respect to E. Okay, and you can see that the result is distributional because you have a delta function in the result. Okay, this page. All right, so we finished the calculation for flux. So let's compute the functional derivative of holonomy with respect to A. Okay. Now we use the this formula for holonomy using we divide the holonomy into small pieces, and then we write the holonomy as a product of small holonomies, smaller, shorter holonomies, and we can linearize the shorter holonomies. 1 plus integral delta S1. So let's say a generic factor in this product is delta Si is on the small segment delta Si. And the last one is 1 plus delta Sn. Okay, so here we should understand this formula that n goes to infinity. So in the limit that n goes to infinity. Okay, and so here As is A, B, J, X, S. Yeah, so it is the field evaluate along the curve dot B half tau I. Okay. So firstly, so we can see that if X do not belongs to the edge, yeah. So because this is a functional derivative, it should act on certain A's, and all the A's in these factors are along the edge. Yeah. So therefore, if X do not belongs to edge, the result is just 0. It equals to 0. Okay. Because the holonomy is supported on the edge, you are taking functional derivative at another point, then of course you get 0. And if X belongs to edge, then you don't have 0. Okay. Let's say then this X, let's say this is the edge and this is point X. Then because we have subdivided this edge into small segments, then this X must fall into one of those segments. Well, let's say this segment is Si. Then what you get is 1 plus. So it doesn't affect other factors. It only acts on the segment Si. Well, you just have integral delta Si. Well, this term is because it is a very short holonomy. We have linearized this holonomy already. So and it is linear to A. Yeah, then this functional derivative is very easy to compute. Yes, delta I delta AB E dot Y half, and then you have a 3-dimensional delta function. X. Okay, and also the other factor followed in the following. In the end, you have 1 plus delta Sn. Yes. Okay, so now you have to because all these formula is understood in the continuum limit, in the limit that n goes to infinity, that these segments are infinitely refined. Then once you infinitely refine those segments, you find, and then you have basically this part is a holonomy of E1. Well, it's one of the is holonomy, and then the part in the end is also holonomy. Basically, those factor here before this factor, you got one holonomy. In these, we denote, let's say H E1. Well, on my note, I said it is E1, but let's say this is E. What should I do? So let's say this is 1 to x, and the part, those factors after these this delta, this factor here, it is will be h x. Sorry, this is 0x, h0x, and this is x1. Okay, it means, well, this just means that you have an edge parameterized from 0 to 1. So 0 means the source, and 1 means the target, and it's oriented. And this just means the holonomy running from 0 to the point x. And this is the second holonomy is the holonomy running from x to 1. Okay, I hope this is clear. And this is, well, clearly coming from the factor, all the factors before the factor we act on functional derivative is just the combined, same as before, become h0x. And the factor after the factor where we did functional derivative also combined together as before, become a hx1. All right, so now we can write more explicitly. We can pull out the integral ds, and this integral is over delta si. But since you are integrating a delta function, you can freely extend this integral. You can freely extend the integral from 0 to 1. Yeah, because the only part which contribute is delta s1. So it's fine to extend. So I pull out all the non-matrix valued terms. Well, probably, yeah, because I use coordinate y, probably here it's better to use y instead of x. So for coordinate y, so and then h0x tau half hx1. Okay, that's the result. And now let's use the special coordinate. Again, we have introduced the coordinate, and here we assume that this y1 is just the parameterization of holonomy of this edge. Yeah, this edge we can choose a parameterization, right? So here we choose the parameterization s, but I can just set the parameterization s is just y1. So let's say s is just equals to y1. Okay, and then this delta function, we can again write explicitly this delta function. So this ds is just the dy1. E dot a is just partial y is just a tangent vector of e, and so it's just the coordinate basis partial y1. And you have a delta function. Delta function you can again write it as write explicitly as a three-dimensional delta function. So this is just the delta x2, delta x3, delta x1 minus y1. All right. So because here x and y is just well, you write it as x1 minus y1. Maybe one step in between, x2 minus y2, y2 minus y3. But along the edge, along this edge, y2 equals to 0, y3 equals to 0. Look at this picture. So along the edge, y2 and y3 are equals to 0. Okay, and the rest. H 0x tau half. Okay, so now we can integrate out integral of dy, yeah, and dy1 because we have a delta function x1 minus y1. So now the integration, so the result is well, partial y1 a delta x2 delta x3 and let me see. So h, well, 0. Well, this is just the h again. H 0 x x1. Yeah. So because it's only dependent on x, independent of y. Okay, so this is the result. And one remark is that clearly in this formula, I use abstract index. I take A as abstract index. But suppose, but I think you see in the computation of PJ, well, in this formula, I take ABC as a component index. You see, I let well, in this formula, you see, I let VC D just be 1, 2, 3. Well, BC is 2 and 3. Clearly, in this formula, in the Flux formula, I use ABC as a coordinate index. Okay, but in the calculation of Holonomy, I use it as abstract index. Well, to translate, it is very easy to translate this abstract index to coordinate index. So once I do it, so this guy will be just delta A1. Will be just delta A1. So